LeChatelier's principle. LeChatelier's principle is also known as the equilibrium law. Americans usually say LeChatelier's principle. And this is basically a set of rules that allows you to tell how an equilibrium will be affected by a change to the reaction, any kind of change. So let's talk about these. So this was Henri Louis LeChatelier, and independently Carl Ferdinand Braun, a German scientist. And what LeChatelier said was a system at equilibrium, when subjected to a change, and what he means by change is a change in concentration of a reactant or a product. You add some reactant, you take away some product or whatever, or a change in temperature, a change in the volume, especially if you have gases reacting, or a change in pressure, also for gases. And he says that if you have one of these changes, the equilibrium will readjust itself to counteract that effect and establish a new equilibrium. So, for example, the famous Haber-Bosch reaction I've shown you a couple times before. We have two reactants, nitrogen and hydrogen gas, to produce ammonia gas. And you'll notice all three are gases, so they are part of the mathematical calculation for equilibrium. So we look at all three. So let's ask ourselves, what will happen to the equilibrium? Will it be pushed to the left? Will it be pushed to the right? In other words, will it favor more products or will it favor more reactants if I change something, or will it have no effect at all? Well, if I added more nitrogen, N2, I have more reactants, so it's going to push the reaction to the right because initially I'll have too many reactants, so I need to make some products. So the equilibrium will shift a little to the right. And if I remove H2, that's one of the reactants, if I'm taking away reactants, I'm dropping the reactant concentrations, and therefore I have to make more reactants to balance it out. And that means that some of the product will be turned back into reactants to make up for that H2 that was missing. So this will shift to the reactants or shift to the left in the equilibrium. If I increase pressure or decrease volume, these are things that affect gases. So we look at the gases, and it doesn't matter what the gases are, it only matters how much of the gases are on both sides of the equation. Well, on the left side of this equation, our reactants, we have 1 nitrogen and 3 hydrogens. So if this was in moles, that would be a total of 4 moles on the left side of the equation. Our products are 2 ammonias, or 2 moles of ammonia gas. So we have 4 moles of gas on the left, and we have 2 moles of gas on the right. If I increase the pressure, which side will be favored? Think of this as in a closed container. If I suddenly increase the pressure, which is a more stable position? To have a lot of moles of gas on the left, or only a little bit of moles of gas on the right? Well, increasing the pressure will favor the right side. There are less moles of gas that's able to handle an increased pressure. It's a lot easier for 2 moles to be under pressure than for 4 moles of gas to be under pressure. So pressure will always favor the side with less gas. Likewise, decreasing the volume does the same thing as increasing the pressure. If we haven't learned about that already, when you get to gas laws, you'll hear about a law called Boyle's law, which says when pressure is increased, volume decreases it. Think of it as squeezing a container tighter. That increases the pressure. So decreasing the volume of the container will necessarily increase the pressure. So decreasing volume and increasing pressure will do the same thing. They will always favor the side with less gas. So this will also favor a shift to make more products, because 2 moles of ammonia take up less space than 1 mole of nitrogen plus 3 moles of hydrogen gas. So let's look at an example here. This is a generalized example. So there's no specific reaction here. If we increase the reactants will always make more products. We need to make up, we've made too many reactants relative to the products. Remember, the equilibrium is a mathematical balance of the products and the reactants in some way. And if we have too many reactants, we need to make more products. If we decrease the reactants, we need to make more reactants. If we increase the products, we need to make more reactants also. And if we decrease the products, we need to make more products. So each of these will always be the case as long as the reactants and the products are actually in the mathematical expression for equilibrium. In other words, these rules only count if we're talking about gases and aqueous solutions. They will not count if it's a solid, a pure solid, or a pure liquid. They will have no effect. Increasing pressure and decreasing volume will always favor the side with less gas, less moles of gas. Likewise, decreasing pressure will make it easier to have the side with more moles of gas. Increasing temperature or decreasing temperature, these will depend on which side the heat is. If we have a reaction that produces heat and we're adding more heat by increasing the temperature, we have just added another product, and we don't want to add more products to something that's already making heat, so this will drive the reaction backwards. It'll drive it to the side with no heat. It'll drive it to the side with less heat, which is the side that for an exothermic reaction will be the left, for an endothermic reaction will be the right. And likewise, decreasing the temperature, you're removing heat. Whichever side heat is, if heat is a reactant and you're removing it, you will favor reactants. If heat is a product in an exothermic reaction, you will need to make more heat. So you have to be careful which side has the heat. That will tell you. Just think of heat as a reactant or a product, depending. It'll be a reactant in an endothermic, it'll be a product in an exothermic, and it follows the exact same rules as the product and reactant rules at the top here in red and blue. Adding a catalyst. A catalyst speeds up reaction, but a catalyst also speeds up both the forward and the back reaction by exactly the same multiple. If I add a catalyst that speeds the forward reaction up 1,000-fold, it will also speed up the backwards reaction 1,000-fold. So it has absolutely zero effect on the equilibrium. It'll make it get to equilibrium faster, but it will not change what that equilibrium is. So a catalyst will have no effect in any case. So here's an actual reaction. 2 moles of nitrogen gas react with 1 mole of oxygen gas to produce 2 moles of N2O. This is dinitrogen oxide, also known as laughing gas, also known as nitrous oxide. So in this case, heat is a reactant. This is an endothermic reaction. It actually feels cold to the touch because it is removing heat from the surroundings. So in this case, because it's endothermic, because the delta H is a positive value, it's heat you have to add to make the reaction go to the right. We think of this as a reactant, and keep that in mind when you look at the temperature changes. So the first question, what happens when you increase the nitrogen gas concentration? Well, that's a reactant. We have too many reactants. We need to make more products. Decrease the oxygen, removing a reactant. We need to make more reactants. Increasing the N2O. Well, if we're increasing it, we have too many products. We need to make more reactants. If we decrease the N2O, we have too few products. We need to make more products. Now, pressure depends on how many moles of gas on the left and the right. On the left side, we have 2 moles of nitrogen, 1 mole of oxygen. We don't care that they're nitrogen and oxygen. We just care that we have 3 moles of gas on the left. And we have 2 moles of nitrogen dinitrogen monoxide on the right. So the 2 moles of dinitrogen monoxide, that's 2 on the right. So it's 3 on the left, 2 on the right. If you increase pressure, we always favor the side with less gas. So that's the products. If we decrease pressure, we'll go the other way. Now, if you have trouble remembering decreased pressure and you're having problems thinking about decreasing pressure, decreasing temperature, if it's easier to think about increasing, figure that one out first and then switch your answer to the opposite answer. So I hate thinking about decreasing pressure. I think about increasing pressure. Increasing pressure favors the side with less gas. So if I'm asked about decreasing pressure, I figure out increasing first, and then just flip my answer. And you can do the same thing with temperature. If I increase the temperature, that means I'm increasing heat. Heat, in this case, is a reactant. If I'm increasing a reactant, I need to make more products. And if I'm decreasing a reactant, I need to make more reactants. And as always, adding a catalyst speeds up both reactions. It makes it get to equilibrium faster, but it doesn't change what the equilibrium is. No effect from a catalyst. Okay, let's look at one more example. This is a reaction of zinc metal with hydrochloric acid. You should be familiar with this one already. It's a classic single replacement reaction, forming zinc chloride and hydrogen gas. This is an exothermic reaction, which means it produces heat. So its delta H would be, its delta H, meaning a change in enthalpy, is minus 153.9 kilojoules, but we're just going to simply write it as a 153.9 kilojoules as a product. It's just another product in the reaction, and it's best to think about it as a product in order to look at LeChatelier's principle. So let's look at some of these problems. What happens when you increase the hydrogen chloride, the hydrochloric acid concentration? Well, that's a reactant, so you have too many reactants now, you need to make more products. If you decrease the zinc chloride concentration, well, zinc chloride is an aqueous product. We're decreasing a product, we need to make more product. Increasing the zinc. Zinc is a solid reactant. It's a reactant, but it is solid. It's a pure solid. And as a pure solid, it does not affect the equilibrium. So it will have no effect. Pure solids and pure liquids, just like in our calculation of our KEQs, has no effect on the equilibrium if you change how much zinc. If you throw in another chunk of zinc, it's not going to shift the equilibrium. If you remove a chunk of zinc, as long as there's a little bit of zinc in there, it's still the same concentration of zinc. It may not be the same total amount, but it's the same concentration. So by adding zinc, we're not really adding the concentration, and probably shouldn't have concentration bars there around the zinc, the brackets around the zinc, but we're not increasing the zinc. We can't increase the zinc concentration. Increasing the hydrogen gas concentration, well, that's a product. Now we have too many products, we need to make more reactants. Increasing the pressure, well, anytime you see pressure, we have to look at the gases. There are no gases on the left side of this equation, and there is only one gas on the right side, 1 mole of hydrogen gas. So we have 1 on the right, and we have 0 moles on the left. Increasing pressure will always favor the side with less gas, and that would be the reactants. It has no gas. If we increase pressure, it's easier for the reaction to go to the side that doesn't produce pressure from gases than the side that does. Likewise, decreasing pressure will always do the opposite. Increasing temperature will depend on whether it's an exothermic reaction, which this is, where the heat is a product, or an endothermic, where the heat is a reactant. Here, the heat is a product. We're adding more heat. That's like adding more product, and therefore we need to make more reactants. Likewise, decreasing the temperature will do the opposite of increasing the temperature, which is forming more products in this case. And then finally, increasing nitrogen gas concentration. We'll look at this reaction. Nitrogen gas is not involved. Nitrogen gas doesn't react with any of these, and it's not even part of the reaction, and therefore it should not have any effect. And with this, we'll stop here.